This tutorial will look at the bearing pressure at the base of shallow foundations. Bearing pressure is the contact force per unit area across the bottom of foundations. It's pretty important because it's the basis for soil bearing capacity and settlement. In general, there are two loads we have to consider. One is from the superstructure P, the other is the self-weight of the block. The distribution of the pressure depends on a variety of factors: soil properties, applied loads, rigidity of the structure, etc. But according to St. Venant's principle, we can consider it to be uniformly distributed for simplification. To illustrate, let's have a look at some special cases. In the first case, we have a footing perfectly flexible, so it bends as necessary to maintain a uniform bearing pressure. The lower two figures show footings with a EI approaching infinity. If the footing stands on sand, the distribution of bearing pressure might appear to be a parabola because the sand at the endpoints can be squeezed out, making the central part bear much more. Whereas if the footing by soil is clay, the distribution appears to be a saddle shape. This is because as a rigid body, the settlement anywhere must be in sync. But the higher pressure at the endpoints can result in a soil failure, and it's pretty much like a rigid footing standing on the sand. So ultimately, the distribution shape will become a parabola. So next, we'll look at the calculation of the bearing pressure. Due to the simplification, what matters is the magnitude and eccentricity of resultant force. So here we have a vertical load and possibly a bending moment. So as is mentioned before, the vertical force is comprised of two components: the P from the superstructure as well as the self-weight of the block. You may calculate it by proportion or use a general unit weight. So first, let's look at the applied load at the base with no eccentricity. It is clear that the magnitude of the pressure is equal to Fv over the area, which is L times B. There's no doubt about the area of the square footing, but when it comes to the continuous footing, we have to use a unit length instead of the L. So the area is B times 1, which is what you have to pay attention to. We also have to take into account the water uplift if the groundwater table is above the base of the footing. We'll have to minus the buoyancy above the footing base after calculating the bearing pressure. Now let's look at the bearing pressure when the applied load is with one-way eccentricity. What we have to do is to calculate them separately, and after that superpose them together. So the pressure generated by Fv is Fv over the area, and the maximum pressure caused by the bending moment is m over w. For a squared cross-section, the w, which is a section modulus, is equal to b l squared over 6. And now we can combine them together. So we have P max here and P minimum here. Because we don't know about the magnitude of the pressure generated by M, so we have to discuss several cases. The extreme pressures equals to V over the area plus or minus the bending moment over the section modulus. and it equals to FV over BL in brackets 1 plus or minus 6 times E over L. So now we make the eccentricity the only factor influencing the value of P minimum. If what's in the bracket is positive, the bearing pressure distribution is trapezoid. If it's 0, it's a triangle. But if it's negative, it's not like what you might have thought. We have to consider a redistribution. So let's draw a footing here by resultant force with an eccentricity E. Let's define the distance between the applied load and the edge of the footing as K. So it equals to L over 2 minus E. So the bearing pressure is distributed as a triangle, but not across the whole base of the footing. This is because there can't be any tension at the interface between the foundation and soil. Instead, the footing will be lifted off the ground, and the part of the footing remaining on the ground is with a length of 3K. So the next tutorial is expected to be with some examples related to what we have talked in this tutorial, and also there will be something related to the two-way eccentricity